Okay, so now we move to chapter 11 on fractal. All right, fractal. Now, fractal are complex geometric shape objects with a fine structure, at arbitrarily small scale. So that is a generic definition. Fractal are complex shape object with arbitrary with fine structure, arbitrary small scale, and they usually have some degree of self-similarity. Now they have a great interest because they are very beautiful. Okay, first of all, some of these fractals are very pretty, particularly the mandelbrot set, which later on I'm going to show. It's very pretty, and it's, on one hand it's very pretty, but on the other hand it's very complex and it has endless structure. So they are reminiscent of nature's object. One of the things often in nature object mentioned is a coastline, for example. Coastline, you know, it's a zigzag, and you zoom in, it's a small zigzag, and so on. Mountain range, a cloud, a blood vessel, for example, in our human body, is in fact has symmetry. Your lung, for example, the lung air, you know, if you look at your lung structure, you have big vessel, air pipe, and then go to smaller air pipe. So you take a piece of broccoli, for example. If you zoom in on a broccoli, you can see a tree, for example. You get big branch and a small branch and a teeny branch and so on. So this fractal behavior happens in a lot of natural things. And the fractal is a mathematical way you can describe of this object. One of the people who is early proponent, and in fact, I believe coined the phrase the fractal, is the Mandelbrot, who was I think a computer scientist actually at the IBM at the time when she did all these things. I remember I read the book when I was graduate students, which in the 80s. So if you can look at a Mandelbrot book if you have not. Probably these things now are online available somewhere. Now, to get the systematic start on the concept fractal, let's start with something simple. And the first concept we want to introduce is something called countable and uncountable. Now there are set, you know, the set is fundamental concept in mathematics. Set is basically collection of objects. A collection of objects can be countable and uncountable. So, you know, like all the people today in our Zoom section, we have 5 of you guys plus me, 6 people. It's countable. You can count 1, 2, 3, 4, 5, 6. Cantor was the first one which really introduced the concept this countable and uncountable set. So, particularly when you have set which is infinite. Now, how do you know infinity is something countable or not? So here is his definition. So say the two sets are equivalent, has same cardinality. A cardinality is basically say number of elements, number of objects in that set. You say two sets are same if you can find one-to-one correspondence, between two sets. Then we say this two set has same number of countable. Have a same number of objects, Here's a simple example. A natural number like 1, 2, 3, 4, 5, all the way to infinity. We say this is a countable number. It's a countable because we have a way to arrange this object in certain particular pattern, such that for any object in the set, we can find it in a particular position. We can locate it in the position. So for example, for natural number, it gives me arbitrary natural number, like say 1001. Then I can find 1001 in this set because I know it's a position in this set. It's 1001 position in this set. Okay, so that is something what we mean by countable. Countable is now everything which can be mapped into something like this. then it's countable because there's a one-to-one mapping, for example. So if another set X can be put into one-to-one correspondence with a natural number, then we say that set is countable. Otherwise, we say it's uncountable. So, do you think that all even number is countable or not? Anybody? Wait?
Yeah, I think so.
Countable or not?
I think so. It's countable.
How you say even number is countable?
Like we can rearrange them to be like 1 correspond to 2 and 2 correspond to 4. So like I cross K
even number is
to
countable. Very good.
Yeah.
Matthew, what do you think about what about all the integer from -infinity to +infinity? Is that countable or not?
Yes.
So how you count it?
So you want to list them in an order where like where you just have like one trailing end, so you can have 0, 1, -1, 2, -2, 3, -3, like that.
Okay, that's very good. So you guys either smart or you read some of these things. All right, so even number, of course, you can map 2 to 1, 4 to 2, 6 to 7, and the same thing with all integer. All integer, if you arrange in this order from in terms of magnitude, just switching back and forth between negative and a positive number, then you have a particular unique sequence. Every integer, you can find a particular position in this sequence. So therefore, integer is countable. And here's the tricky part. What about all the rational number? Why? What about rational number? P over Q. Is that number is countable or not? I see Brian is drinking, but his mic is mute. I cannot hear you, Brian.
Sorry. Yes.
So you think all the rational number is countable?
Yes.
Okay. Indeed, it is, but it's a little bit more tricky how to arrange this. So to see whether you can you guys can understand that they how we arrange all the rational number into countable. So here's the way is you make a table. So if you have a P over Q, a rational number, remember rational number is a ratio of the two integers, right? Two integers. So you make a ratio. Let's just say for a moment, just positive number, positive rational number. So basically, you create a table where the low indexing is Q, the column index P. So in this way, it's P. So this line, this row is all corresponding P equal to 1. This column is all corresponding to Q equal to 1. This row is corresponding all the P equal to 2. So that's how you arrange it. So let's say you have 3 over 4. So which will be the element 3, 4 in this table. So the third row and the fourth column, right? So therefore, all the positive rational number has a unique position in this table, in this infinite table, right? And then to map this infinite table to the natural number, you start arranging. Okay, this is the 1, 2, 3, 4. You just go diagonal. So this is a unique way to arrange this sequence. So if you know P and Q, then you know in that sequence where exactly that number is. So you can map into the whole number, into the whole number, the natural number. So this is interesting, right? So you know. You know, on one hand, there are more even number than there's less even number than the integer because exactly half of length. On the other side, we say they are exactly the same number of length. So that is because they're all countable. So that's why, I don't know, some of you probably had read some of this puzzle or wider things which people have been showing. I think you can add, say, 1, 2, 3, 4, add all together equal to 1/12 or something like that. Some of you have saw those puzzling, that you can add all the number equal to 1/12.
Yeah, I've seen that.
Yeah. So it's all had to do with manipulating all this countable. You can make it countable to be same number, even though you say even number and the whole number, they clearly on one side, you can say one is twice the number, many of the other one. But if you do this mapping, they are exactly the same number. So here, so therefore, this is countable. Now, all the real number between 0 and 1, on the other hand, is not countable. Now, this will take a little bit of work to really to understand this, to how to actually prove it, even though it makes sense. So I'm going through this with you. So to say solution, the proof is a proof by contradiction. So all we need to say, assuming it is countable. So let me say, assuming we can arrange all the number between 0 and 1 in terms of some sequence, some particular unique sequence. Right? That's the definition of a countable. Now, every list number, we can rewrite it in terms of the decimal. So x1, remember, is a real number. So 0, for example, if x1 is 0.943. So this will be x11 will be 9. So this now is integer. x11, x12, x1. So this is all now integer between 0 and 9. Right? So basically, there is a digit. So we write out in terms of digit. So each of this number we write down as a digit. So xij denote like j's digits of the real number xi, assuming all the real number can be arranged in terms of sequence, is countable. Then all we need to do is to say we construct a real number which is somewhere between 0 and 1, but it's not in this sequence. All we need to say we find another number which is in between 0 and 1, which is not this sequence. Then it's a contradiction. Therefore, it's not a countable number. So the way you construct this number is to say is the following. So you construct a R which is given by this digit. So you can say is 0.x11 bar, x22 bar, x23 bar, where x11 bar denote that any number between 0 and 9, but it's not x11. So for example, if this is a x11 is 9, x11 bar will be any number 0 to 8, but not 9. So x22 is 3, for example. If x22 is 3, then x22 bar will be 0, 1, 2, but not 3, but 4, 5, 6, 7, 8, 9. Are you all getting that? How this x bar is constructed? I don't hear any of you guys respond.
Yes. Yes.
So this R will be 0.x11 bar, x22 bar, x33 bar. By definition, of course, this is a real number, which is between 0 and 1, right? Because it's 0 point something. But 0.x11 bar cannot be in this sequence. Well, because it's not x1, right? Because this digit is different from x1, and it's not x2 because this digit is different from x2, and it's not x3 because the third digit is different from x3, and so on and so forth. Because we construct this xr with infinite digit, every digit is different from the diagonal of previous of this things. So therefore, this r cannot be in this sequence because by way of construction. Therefore, this r is not in the sequence, but it is between 0 and 1. So therefore, it's a self-contradiction, and that's why we say real number between 0 and 1 is not countable. It's not countable. So it's kind of neat trick. Now, And here now is another set, which is called Cantor set, which has an interesting property, has a zero measure, but it's not countable. Now, the real number between 0 and 1 is understandable. It's not countable because it actually has a finite length. It's a finite length. And here is how we construct Cantor set, which is actually the first fractal we're dealing with. So just pay attention. It's actually pretty straightforward. We take a number axis between 0 and 1, right? All the possible number between all the real number. We divide it into 3 sections: 1/3, 2/3, and so first third, second third, and third third, right? We cut off the middle section. So we start with S0, which is a complete set of number between 0 and 1. We cut out the middle one, that we call S1. That is the first iteration. And next iteration, we take each of this remaining set, repeat the same thing. So this 1/3, we cut into 3 segments. We remove the middle segment. This one, we repeat the same thing. This segment, we divide into 3 segments. We remove the middle segment. So that gives you a second iteration. And then we just repeat these things indefinitely. So next iteration, we take any remaining segment, we divide into 3, we remove the middle one, and the same thing. So S3, S4, same for. And then we iterate this to infinity. Whatever remaining is what defined as a Cantor set. Cantor set is the C infinity or this S infinity. That's called Cantor set. Is that clear for you guys? How this Cantor set is constructed?
Yes.
Yeah.
Yeah. Okay.
Yes.
Now
Most certainly.
the limiting set is called Cantor set, and this set is a fractal. Now, it also has fractal because it already has the self-similarity. So if you zoom in these things, in fact, if you zoom in this section, it looks like a big section, right? If you zoom in this section, it looks like a whole big section too. So every small detail, doesn't matter how small scale you zoom in, it has exact, in this case, in the Cantor set, has exactly the same similarity as a larger set. So that's number one. So it gets several properties. Cantor set has structure at arbitrary small scale. It's clearly doesn't matter how small you go into it, it has a structure. It contains small copy itself in all the scale. In all the scale. And it has a dimension which is not an integer. We will come back to in the next lecture to define this called fractal dimension, the dimension of fractal object. In fact, it's dimension 0.63. It has a zero measure. Cantor set has zero measure. It's consistent of uncountable many points. This is a little bit non-obvious that it is uncountable. Zero measure seems to make sense because if you look at it, you keep cutting the length out of it. You keep cutting length out. So what remaining actually has infinitesimal length. It has zero length. So you can show the length of remaining one is very easy, right? Because you started with 1. After 1 iteration, you get 2/3. After 1 more iteration, you have 2/3 of 2/3 remaining. And after nth iteration, you have 2/3 of the nth power remaining. That's in terms of the length. And as n go to infinity, this length go to 0. So the Cantor set has zero length. Has a zero length. It's a little bit non-obvious, but actually to show that this Cantor set actually it has the Cantor set is uncountable. But the way we show is uncountable is just like what we did before. We construct a set contradiction. So to show the Cantor set is uncountable. The idea of that is to expand Cantor set in terms of base 3. This is actually the first time we're dealing with base 3. Now you're all familiar with base 2 and base 10 number, right? So
Yes.
if you take any arbitrary number x. The way you expand the base 3 is basically divided by 1/3. Whatever is the whole number, the quotient is a1, and then the remaining you divide it by 1/3 to the square. Whatever quotient you get a2, and then a3. So basically, any number x can be, this is now we're talking about between 0 and 1, can be expanded in this fashion. Is, you know, some integer a over 3, another integer over a 3 square, and a cubic. So now in terms of base 3, this is how you write the x equal to a1, a2, a3, and so on and so forth. Okay, so that is how you base it, you expand it in terms of base 3. So a1, a2, a3 are either 0, 1, 2. Okay, in the case of binary is 0, 1, but in the case of base 3 is 0, 1, 2. Now it's very easy to see how the Cantor set number can be written this way. For example, if you have a number which is in this region, the first decimal is 0. If the number is in here, the first decimal is 1. If the number is here, the first decimal is 2. Right? Because we divide into 1/3, 1/3, 1/3. Now, for number which is with the first decimal is 0, the next decimal, whether it's 0, 1, 2, again, it depends on whether it's a left 1/3, a middle 1/3, or right 1/3 of this segment. If it's a left 1/3, then it's a digit. The second digit is 0. If the middle 1/3, the second digit is 1. If the right 1/3, the second digit is 2. Okay? And then you can continue this process. If the number is, for example, is here, then the third digits depend on whether it's the left 1/3 of this or right 1/3. Okay, and go on. But the Cantor set, of course, cannot belong to middle. So Cantor set is this white region. So therefore, you can see the Cantor set has a digit which is never 1. Is that clear? It's either 0 or 2. Because this is Cantor set is a corresponding digit either 0 or 2. If you keep going, the Cantor set, if you expand it in terms of base 3, then it's always 0 or 1. It never has a digit which is 2. Right. So the Cantor set consistent of all the points whose base 3 expansion contain no 1. Right? Is that make sense to you guys?
Yes.
Yes.
Yeah. Okay.
You just
Now we can write another number. So now we can show that it's uncountable. And this is so you create a number. Suppose it's countable. So it's basically the same thing. Suppose it's countable, which you can say you can write in certain sequence, C1, C2, 3. Now I can construct a Cantor number, which is belong to Cantor set, but it's not belong to this sequence. So you construct same thing. You construct C bar, which is C11 bar, C22 bar, and so on. C11 is, remember, is the C1 expanded in terms of base set. C11 is the first digit. C22 is the second digit of the second number. C23 is the third digit of the third number. And then we construct a new number, which is C11 bar, C22 bar, and so on and so forth. Okay. Now this number, then so this number is in the Cantor set, where the other bar means we switch between 0 and 2. So CMM bar equals 0 if CMM is 2. So basically, if C11 is 0, then we say C11 bar is 2. If C22 bar is 2, we say if C22 is 2, then C22 bar is 1, right? C22 bar is 0. So basically, these are either 0 or all these digits are either 0 or 2. Therefore, it belongs to Cantor set. It belongs to Cantor set. But it does not belong to this sequence, because by definition, it's none of this number, because we construct it such that they normally, at least there's one digit which is different from each of these numbers. So that's how we show Cantor set is uncountable. So here's the interesting property of a Cantor set. This is what it is. You know, the Cantor set go to infinity is a fractal object which has self-similarity, has a zero measure, but is uncountable. And I think that's where I'm going to stop, and then we'll come back on Thursday to define rigorously what we mean by fractal dimension of the fractal object. And that, I think, will be all for today. Anybody got questions? No question? Pretty straightforward, huh? If no question, I'm going to stop here. And again, I'm going to postpone the due date of the color homework by Thursday. And then I think then the week after that, probably is another set homework due. Yes. All right.
Okay.
Okay.
Okay. Bye.
Thank you.
Bye.